Hi, it's Robin. I've got here a neat little basic demo. I'll just give it a list. Written by Simon Stelling, aka S.E.S. of the group Genesis Project back in 2008. So it's a basic program, and as you can see, it fits on a single screen. We'll look at the code in depth in the rest of this video, but first, of course, we'll give it a try. I'll clear the screen and type run. Okay, so again, this is just written in BASIC. In case it's not obvious what's going on, this is showing 16 sprites, hardware sprites, at once. The Commodore 64, or specifically the VIC-II, the video chip, only has 8 hardware sprites. So this program is doing something called Sprite Multiplexing, that is, reusing the hardware sprites dynamically to show more than the usual limit. In this case, 16 sprites. Now, this usually requires machine language to pull off because BASIC is far too slow to dynamically reuse the sprites as the screen is being drawn. But somehow this program manages it, so we'll try to figure it out today. Now, one funny thing is that this program, not only can you not stop it, you can't even hit stop restore and get out successfully. But fortunately, if I reset here, I have my super snapshot active, and I think this will work. If I go greater than and the pound symbol, it'll engage the basic plus 1.1. Then I can type in the old command and list. And there's our program back again. So that's a funny quirk. The program really is all written in BASIC, but it's doing some pretty nasty tricks. And this poke 648 is in the heart of not being able to reset the computer. I should get back to that. Okay, so the rest of the video, we're going to be looking at how this basic program accomplishes 16 sprites on screen at once. How does a basic program do sprite multiplexing? Okay, so let's just walk through the program. Line 1 just says go to 4, and rather than walking through it in line order, we'll walk through this in program execution order. So we're just going to follow go to 4. We're going to skip lines 2 and 3 for now. They're very important, but we'll get back to them near the end. So we'll go ahead to line 4 here. Now, this is just a loop from 0 to 7. And it's doing two things. It's setting the sprite pointers, which are located at 2040. It's going to set all 8 of them to the same sprite, number 15, that S sprite we saw on the screen. And then it's just going to go next. So that's just very typical basic code. And then for I equals 0 to 62, we're going to read in a data statement into variable X. And then we're going to poke into memory at 960 plus I. So this is just reading 63 bytes in from the data statements, which are down here, and poking them sequentially into memory from 960 to 960 plus 62, whatever that is, 1022, I guess. Okay, so what's special about 960? Well, if we divide that by 64, then we get 15, this value right here. That's the sprite pointer. The VIC-II video chip has 16K of video memory, but shared with the Commodore 64. So actually you can position it in one of 4 spots. 16K goes into 64 4 times. This program's just using the default, the lowest 16K. These sprite pointers come in 64 byte blocks. Each sprite has 63 bytes, but they start at 64 byte boundaries. This is poking in the pixel data into video memory and then pointing all 8 sprites at that same definition, that S character that we saw on screen. And to look at those data statements, they're here, and you just see each one is a byte from 0 to 255. The only real trick here is that there's commas sometimes. Usually commas are used to separate the numbers, but if you just put a comma without a number before it or between, in this case here, then it will just kind of imply a 0. X will just be set to 0 in that case. So that's just a slight space savings. And actually, I went through, I think this extra comma is unnecessary because it actually in total defines 64 bytes, but only 63 are needed. Not to nitpick or anything. Okay, so line 4 handles the sprite definitions. Line 5 pokes 648, 208. Now, location 648 is a kernel operating system variable. It contains the starting page of video memory. On 6502-based machines, we talk about the machine having 256 pages of memory, and each page is 256 bytes. 256 times 256 is 65,536 bytes, or 64 kilobytes. Normally, screen memory is at location 1024. That's the starting position. Up here in the top left corner right now, this is memory location 1024. So if you divide that by 256, so let me erase that. If you divide that by 256, you get 4. So that means that normally screen memory starts at page 4. So normally this would be poke 648, 4. Well, that's the default anyway. So we're changing it to 208. If you divide 208 by 16 to find out the first hex digit, it's 13, which is D in hex. So that means that this 208 is actually pointing screen memory to D000 hex, or 53248 decimal. Well, you might know that that is the address where the video chip lives. So that's very unusual, but it's the key to how this works. Now note that poking 648 doesn't actually tell the video chip where screen memory is at all. All it's doing is telling the kernel where in memory it should be putting information for its print statements. The VIC and the kernel really don't care if each other are looking at the same thing. The kernel just wants to know where it should print, and the VIC just wants to be told what to display. If those don't happen to be the same, they don't really care. They'll still work. The user just won't see what's being printed. So this really is the secret to the whole thing. I've got an example of how this works that hopefully will clarify all this later. Next, poke 56334. This is CIA number 1, control register A. That is, the C64 has 2 input-output chips, both called the CIA. This first one reads the joystick ports and the keyboard, and it's also in charge of firing an interrupt at approximately 60 hertz. 60 times a second, an interrupt occurs that drives the system interrupt. And when we see the cursor flashing, that's how we know that the system interrupt is active right now. So this poke actually kills system interrupts completely, and that causes the user to lose control of the system. You can no longer type on the keyboard, although the restore key does work because that's read separately. It's wired directly into the NMI interrupt. So this poke kills system interrupts, and I think the reason for that is just that the timing on this Sprite Multiplexer is very sensitive, and the system interrupt could be occurring while the screen is being refreshed and cause the Sprite Multiplex display to break down, to not work properly. It's actually a pretty common thing, at least in machine language programming, to disable or control the system interrupt. Next, we're saying variable W to 53266. Now, that is a VIC register that contains the current raster scan line that the VIC-II is drawing, or at least this is the low 8 bits. It's actually a 9-bit register. The 9th bit is located in the high bit of 53265, also known as D011. This, in hex, is D012, and it doesn't actually do anything with it but say a variable because it will be used in a bit. Now, V equals 64. Again, just setting variable V to 64. Likely the reason these variables are being set is because Commodore, Microsoft Basic, is fairly slow at parsing these numbers. When the parser encounters it, it's just a string of text, 53266, and it has to convert that string of text into a number that it can use. And that's a fairly slow process. If you're frequently accessing that register or that value, you're actually wasting a lot of CPU time parsing that value over and over again. When you assign it to a variable like is done here, that parsing is being done once and it gets stored as a numeric value in the variable, saving a lot of time. Eliminates the parsing. So that's being done for any of these variables here. And here's one more, a equals 128. Same thing, we'll see that being used later. Now here is a print statement, and it's printing a whole bunch of characters. You can see it's all contained in this constant string inside the quotation marks. Somewhere around 50 bytes of characters are going to be printed. Now we'll go through this in detail in a bit. You can see here that the first one is a reversed S, which tells the cursor to go home up to the top left corner, and then these @ symbols, and so on. We'll look at that in detail in a little bit, but because this POC648 has told the kernel to print to the VIC-II registers, the I/O registers, this print will not appear on screen. Instead, these values are going to be printed into video registers. A very dangerous thing, but obviously done in a controlled way, they'll have this desired effect of manipulating the VIC quick enough that it can do the Sprite Multiplexer in BASIC. This is definitely cheating and a hack, but this isn't really machine language. It's leveraging the print command. Okay, so we'll get into that in detail in a bit. I hope that satisfies your curiosity enough for now, or at least piques it. Okay, and now we're going to go to 2, and that's those lines that we skipped earlier. Before we do that, here's those data statements we already looked at, and just the remarks down here are the credits. As we said, this was written by Simon Stelling, who I believe is from Germany. Sure looks like it. Okay, so like a lot of other programs, it's doing all the program initialization first. All our video is set up properly. And now when we go to 2, we go right back up here. And this is the main part of the program. I think the only reason that the go-to was introduced was that when we have these kind of go-to 3s as a loop that we'll get to soon, the earlier in the program the go-to occurs, the faster it executes. Although that can actually be avoided with an infinite for next loop. Well, there might be some reason I don't understand. Maybe the timing worked better with this go-to 3. I don't know. So the only reason that we did a go-to all down here for the initialization, I think, was so that lines 2 and 3 would be closer to the beginning of the program. Ideally, you'd have them right at the top of the program, but of course, you want to be able to just type run and not have to type run 4 to do the initialization. So it's usually a necessary concession to have one line to jump ahead over the main loop, do the initialization, then jump back here. Okay, so to look at line 2, we see 4 wait statements, and they're in pairs. Wait W, A, then wait W, A, then a repetition of wait WA, and then wait WAA. We've looked at the wait command before. It's a very strange command, but I'll try and explain it again quickly here. Wait W, that's that location 53266 we talked about. The raster counter that counts from 0 to 255 for the low 8 bits of the screen as it's tracing the screen from top to bottom. Each raster line increments by 1. When it gets to 255, it goes back to 0, but the 9th bit is set. And then on an NTSC machine, it'll do just, I think, about 7 more lines. On a PAL machine, it actually does another 60 or so. And then it wraps back around and starts over again. Oh yeah, by the way, I'm using a PAL machine today because this basic demo only works properly on PAL. Maybe in the future I'll try to fix it for NTSC, but it didn't seem trivial. You're welcome to try and let me know. Right, so back to line 2. So a wait is almost like a machine language super fast peek of whatever this first parameter is, 53266, the raster register. It will AND it with the second parameter here of A, which is defined as 128. So it does a logical AND with 128. As long as that logical AND returns a value of 0, then it will continue to wait. This is the confusing part about it. If right now you're on raster line 0 and you AND it with 128, it returns 0. And raster line 1 returns 0, raster line 50 returns 0, raster line 100 still returns 0. So it'll keep waiting, but then once you hit raster line 128, I scrolled it up, then suddenly it's a non-zero value and the wait is over. And that happens about, maybe not quite halfway down the screen, but close. So to translate this to English, it's wait until we're about halfway down the screen. Then this 3-parameter wait, what it does is it actually inverts. It does the peak of 53266. It does an XOR 128, which has the effect of inverting the high bit and then doing an AND. So it's telling it the opposite. It's wait until the high bit is not set. So that would happen as the raster goes down the screen further. So that'll happen once the raster reaches near the bottom of the screen. Then it waits for about halfway down the screen. Then it waits until it's near the bottom again. And there's probably two just to kind of stabilize things to make sure that the raster is in the position that is wanted. I hope I described that well enough. Note that it's not waiting specifically for raster line 128. It's actually a whole range of 128 possible ones for this wait. You can't wait for a very specific value. You can only wait for one or more bits to be set. Or if you use this version of it, unset to be 0. So line 2 only happens once. That's part of the initialization. That's just kind of getting the basic code in sync with the raster. So it's drawn 2 screens, and it's come down, and it's about halfway down the screen. Now we're going to wait for W and V. And what is V? Well, it's over here, 64. So I believe that has the effect of waiting for raster line 64 or shortly after that. And you can see that's going to be done every frame from now on because all this line contains is that wait, then this print, and then it goes to go to line 3. So this is just a tight loop of waiting near the top of the screen. Raster line 64 is actually just a little bit below the top border, 14 pixels below the top border, I think. Top line is raster line 50. So here's another one of these kind of mysterious prints. And again, it starts with a home and then a number of characters. Okay, so we've explained the whole program except the hardest part, these mysterious prints. So to help explain that, I've prepared another little program here, and I hope this helps, called String Demo. And we'll list that one, and I'll just explain this program here. Line 5 is just something that we'll see in a moment. It just helps make using this program a little easier. Line 10 and 20 are the 2 strings from the multiplexer demo. And I've just copied them exactly as they are and put them in 2 string arrays, index 0 and 1. And I guess you can compare them if you don't believe me, but they, as far as I know, those are exact copies of what was in the basic program. And we're going to use this little program to analyze those. And S equals 1, what was I thinking anyway? That's going to be the array index. So we can modify line 100 to either be 0 or 1, which string number that's what it is, string number we're going to examine. And then there's just a loop here where it goes through to the length of the string we're examining. And it's going to print out each character one at a time. And poke 204, 0 is a little hack that re-enables the cursor to flash even while a program is running. Normally the cursor's hidden while a program's running. And then this is poking into color memory. And this is just a little color highlight that we'll see in a moment just to hopefully improve the visualization. Line 130 is just getting a key and waiting so we can hit enter as we step through this string. Line 140 is a little hack just to make sure that we're doing this cursor hack. This just makes sure that the cursor has stopped flashing before we disable the flash when we move the cursor. Otherwise, sometimes it leaves a stray cursor square on the screen that's ugly. And then poke 204 turns off the cursor hack. Now that's safe. And then we just repeat through the string. I don't know if I had to explain all that, but just so you know. Okay, so when we run the program, it executes line 5, which just prints out run 10 and then lists the program with the text white. Let's just keep it all standardized. And now I can move the cursor here and run line 10, and this will begin our little walkthrough of the string. Okay, so first we're going to look at the second string, which is the one that's actually printed in the sprite demo first. Okay, so if you look on line 20, one of the characters is turned kind of a cyan now. That's the S. So that's what we're currently printing. So that has moved the cursor up to the top left corner. And now you see it's printed that @ symbol on the screen. So what we're doing, this is the exact same print that's going on at high speed in the sprite demo, but instead we're playing it back to regular screen RAM so we can see what it's doing, so you can visualize what it's actually doing to the VIC registers. So it's printing a number of @ symbols. Now, while the @ symbol I think is 64 in the character set, in screen codes, it's actually 0. I'll put a little window up in the corner to show what the screen code is for these characters. And it's that screen code that's being put into the VIC registers. Right now, it looks to us like an @ symbol, but at the binary level, it is a 0. So this is the same as poking 0 into the VIC registers. So you see, it's putting a whole bunch of @ symbols. This is zeroing out the first 16 bytes of the VIC, or actually the first 17 bytes. So what these bytes are the sprite X and Y coordinates. The first 16 locations in the VIC-II registers are sprite 0x, and then sprite 0y, sprite 1x, and sprite 1y. All these @ symbols are zeroing out the sprite coordinates for all 8 sprites, X and Y. And then it gets to one more 0, and that is the 9th bit of the sprite position X. They're all packed into a single byte. There's actually 9 bits of definition for Commodore 64 sprites horizontally. 8 bits wasn't enough, so the 9th bit had to be kept somewhere, so they've packed them up into 1 byte. Now, if you look on line 20, we've highlighted all the @ symbols in blue. These next symbols are cursor right characters. So you see how the cursor is moving, but not printing anything up on the top of the screen now. Well, this is the clever solution. By doing this trick of printing into registers, it has the problem that you might accidentally hit certain video registers that you do not want to hit. So how do you skip them? Just like when you're printing, if you cursor right, it doesn't affect what's in screen memory. So by cursoring right, we're able to move, and actually can go backwards with cursor left and change a previous value if you want. So what's this next one? That R means reverse on. So by turning reverse on, it's going to add 128 to the character being printed. And this allows these print statements to reach a full 256 screen codes. Without using reverse on, it works out that there's only 128 valid values that we can use. It's almost like an escape code in this sense. Reverse on doesn't print anything, but it causes the following characters to have 128 or 80 hex added to their screen code. Okay, so this checkerboard pattern, you see on line 20, the dark part runs from the top left to the bottom right, but what just got printed is the reverse of that from the bottom left to the top right. That's because of the reverse, and the reverse screen codes are 128 more. Normally this code is 7F or 127 decimal, and instead now it's FF hex or 255. Okay, now that next character is reverse off, and this is they're sticky. So the following codes, now that we've turned reverse off, all the values are going to be between 0 and 127. Now there's another cursor right to skip a location. Oh, and I neglected to say that checkerboard, that's 2 characters back. Sorry, I can't go back without restarting the whole program. I guess I should have thought of that when I was making this. That put an FF in location D015 hex or 53269, the sprite enable register. That checkerboard just turned on all the sprites as part of this initialization. And if it's not clear, this whole print is setting up the VIC. This isn't actually doing the multiplexer yet. It's just setting it up. And actually, this isn't completely necessary. I guess it was just used to, because it was cool or easy or whatever. Easy once it was set up. But really, this could have all been done with normal pokes. It's not actually time sensitive, this setup. Okay, so then we cursor right it again, and that skipped location D016, which does things like controlling the X scrolling and multicolor screen mode, screen blanking. So we don't want to change that. And now another 0, and that has gone to location D017, which is the sprite vertical expansion. I guess it's just making sure it's off. It actually doesn't seem like it would be necessary. Then we have 1, 2, 3, 4 more cursor rights, then another reverse on to add the 128. Now another FF has just gone to location D01C or 53276, which is the Sprite Multicolor register. So that has turned on multicolor sprites. And we saw that those S's in the demo are multicolor, 3 colors each. And reverse off again. Yeah, another 0 going to the Sprite Horizontal Expand. 2 more cursor rights, which were the 2 sprite collision registers. I guess no need to mess with those. Okay, and now we've reached location 53280, which is the border color register. And it's putting an N in there. N is the 14th letter of the alphabet, and it happens to be screen code 14, or E hex. And that is the screen color for light blue in the border. So that's why when the demo is running, it has a light blue border, which is also the default. Next is an F, which screen code of 6. That's blue or regular dark blue. That's put in 53281 or D021 hex. That's the background color. That's also the default. And now you see it has 3 X's in a row. And I think that's just saying don't care. Okay, so that's background color 1, which is only used in multicolor background mode. Background color 2, also used by multicolor background graphics. And background color 3, which is only used by the rare extended background color mode. So I think he just put X's in there just because it didn't matter. That P is actually putting a 16 in that register, but because these are only 4-bit color registers, there's only 16 colors, 16 values possible, a P is 16. Well, that's just the same as 0. So it's just saying sprite multicolor to black or 0. I don't know why he didn't use an @ symbol this time, but whatever. And anyway, that's just saying those bottom edges of the letters to black, giving that sort of 3D effect. And now that's sprite multicolor 0. Sprite multicolor 1 is getting an A, which is a value screen code of 1, which is white, top edge of the letters. And now we're in the home stretch. All the following letters, E is 5, color green, and this is going into Sprite 0's color register. So Sprite 0 is going to be green for the main body. B is color 2, red for Sprite 1. And now we're just going through the rest of the sprites. Sprite 2 will be F, which is screen code of 6, color blue. Sprite 3 is G, screen code 7, which is the color yellow. Sprite 4 is H, screen code 8 or orange. Sprite 5, letter M, screen code 13, light green. Sprite 6, letter D, screen code 4, purple, and Sprite 7 is letter C, which is screen code 3, which is the color cyan. Oh, I'm sorry if I made mistakes there. This is way trickier to explain than I thought. But what we have now is a visualization. If we just look across here, these are the same values that have essentially been poked into the video registers. But of course, we're just looking at them on screen memory, so it's easy to visualize. And actually, once that's all done, we could just do a little loop here. For x equals 1024, that's the top left of screen memory, to plus, what is that, to 1051, print peak x, next, oh no, that's not nearly enough, 6071. Sorry about that blooper there. So all I just did here was I peaked those values. If you want to see what actually got stored in memory, there they are, a bunch of zeros. Those 32s are the blanks that were already there, so those weren't actually put in memory. There's the 255, and here's all those colors that were put in at the end. Finishing with that C, which is color 3. Oh, I went one too far there. Okay, so if we run that again, I'm going to set us to, we'll do this a lot quicker. So now we're going to do string 0, and we're going to run this. And now we're looking at the string on line 10. This is the string that's run over and over again during the multiplexer. So it always starts with that home, that reverse S, puts the cursor up in the top left corner to the page pointed at by location 648. And it prints a spade and that 127, reverse on. So this is a whole bunch of values. And rather than me taking all the time to decode them right now, what I'm going to do is go up to this point. Okay, so that is 16 characters that are printed. The next one will send it home again. You see how it just highlighted the S, that means home. And you see the cursors move to the top left. Okay, so if I stop that there, well, it might have left it reversed, but anyway, it doesn't matter much. So you see, we printed a bit more than 16 characters because we turned reverse on, and that doesn't actually cause anything on the screen to be changed. But as I said, it adds 128 to the screen code of whatever's printed. So rather than puzzling over what these are, we know that these 16 values here are the sprite X and Y. They're being blasted into those sprite X and Y registers to position those sprites very quickly. And where are they being put? So I guess I could put a little end there, and just to prevent the program from running this, for X equals 1024 to what? To 1039. And we'll just do that print peak X again. Okay, run 170. By peaking these locations, we've just seen the actual values that are in there. So these are the X and Y values of those sprites. Okay, so sprite 0, I think that's the green one, is at X position 193, Y 127. Sprite 1, that's the second one, is at X 198, Y 144. So all these sprites seem to be further down the screen. So I think it positions the lower set of sprites first, blasts them all into memory quite quickly. BASIC is far too slow to do 16 pokes like this in rapid succession. But this print hack very rapidly pushes all those into memory. Clean that up here. We'll do run 10 again. Okay, so we'll just fast forward through those first 16. Okay, now what's going to do is another set of 16. You see that S sends the cursor back home. That is back to the sprite's zeros, X and Y registers. Then it turns reverse off. If you're looking on line 10, the highlighting. And then it's going to start putting more values in. So this is the second set of X and Y values that position the 8 sprites up at the top of the screen. So there's 2 sets. Each time through this loop in the Sprite Multiplexer, it's going to print 8 sprites, It's going to position 8 sprites using this print, and then it's going to position 8 more. And as the print is executing, the video chip is constantly refreshing the screen, and the timing is just working out right that as it's done positioning those 8 sprites, the video chip is starting to draw those sprites on screen, and it's kind of racing the beam, as the term is called, except instead with assembly language, we're doing it with basic prints. Once it's done those 16, it's going to be ready to start positioning the new ones up towards the top of the screen, and they'll be drawn in as well. So I'm just going to finish doing these 16. Those are the new sets of coordinates, and just like before, we can run line 170 just to print out those values again. Oh, it's not as pretty this time because the X and Y's are smaller. So sprite 0, that's the green one, is at X equals 50 and Y equals 52. Well, that's up near the top left corner. And then the second sprite is at X 80 and Y 53, and so on. These are alternating X and Y coordinates. And this is obviously the upper set of sprites. Okay, I hope that was illustrative. Whoa, this is way harder to explain than I thought it would be, even with all the prep I did. Okay, so let's just load up the Sprite Multiplexer again. Now that we've looked at those strings in great detail, I think we can now see that line 6 is using the print to initialize all the sprites. And then here in line 3, it's using a similar print to blast the sprite X and Y coordinates in. That's a total of 32 values that are getting changed per video frame. And I can guarantee you cannot do 32 pokes. You know, this is running at 50 times a second, the screen's being drawn. So what is that? 50 times 16, 800 pokes a second. Well, the C64 absolutely cannot do 800 pokes a second. It can hardly count in a tight loop that does nothing except increments one variable at a rate like that. It certainly can't do pokes that fast. I actually tried in a separate thing, maybe I'll show the code someday, but the very best I could do without using this print technique, I could show 11 sprites on the screen. I could get about 6 pokes in per frame. That was the best I could do. And just to make sure I explained this well enough, all that demonstration we were just doing in that little program I wrote was printing to the screen like you would normally do. But this poke right here, poke 648, redirects the print away from screen memory and into the video registers. I'm sure you could think of other uses anywhere in memory where you want to rapidly modify memory. You could divert the print routine to any location in memory, really, to rapidly modify memory there. It's a kind of amazing tool, repurposing print into the fastest poke. The fastest poke isn't poke. The fastest poke is print. So we can list that and run it. Display it on top of itself. Kind of hard to make out, isn't it? Oh, and what I didn't explain, boy, this is dragging on and on. So just to explain why this program's kind of like so crashy. Stop doesn't work, but that's because we've disabled interrupts. But normally restore would still work. But the kernel has basically a bug or an oversight in it where when you hit stop and restore, much of the C64 operating environment is restored to how it should be. That's what, the word restore means. Restore it back to operating condition. But on the C64, they forgot to restore location 648. Kind of hilariously, it should get pointed back to 4 because all the video registers are set back. So here, if I hit stop restore, the screen just goes black. Let's see if I can still freeze. I press this, the snappy, go into the monitor, And now let's look at location 648 in memory. Okay, it's still set to D0. So because it doesn't set that back, really it should change it back to 04. When you hit stop restore, everything's set back, but then the screen is cleared and ready is printed, but that isn't going into screen memory in this case. It still is being printed into the video registers. I think it just freaks out the VIC. Well, anyway, here, we'll try this. Let's try exiting. I'll try resuming. It's still broken. Okay. Stop restore now works that I fixed 648, and I bet Super Snapshot even does a little bit of reset itself that helps bring us back. But I think without Super Snapshot, you just can't get out, or an equivalent, you just can't get out of that program. Let's try running it again. Does it still work? Yep, there it is. And I'm not even sure you can do anything in the program itself to fix that. Let's try here. We gotta change that back to a 4, exit, resume, and now stop. There we go. I don't know how this can be solved because the whole way this program works is the super tight loop here. How could you do the poke 648 to restore it when you're the one hitting stop and restore? I guess you could try and add some sort of a check for a keyboard key, but that would probably make everything too slow and the multiplexer couldn't even work. I don't know. And just to point out, just by looking at the similar colors, you can see how the sprites are being reused. In the upper left corner, I can't move the cursor right now. I would use it to point at things, but you see how there's the green S in the top left corner, and then a ways below it is a second green S. That almost looks like a block of 9 sprites together, but there's only 8 sprites possible. So I think the programmers deliberately made that kind of tricky. Once the first green sprite has been drawn, then you can start repositioning it to be reused someplace below it. So even though it looks like there's 9 sprites in a block, you can start moving them so they're staggered like that. Yeah, anyway, kind of clever. Well, quite clever. Okay, thanks to S.E.S for writing that program 15 years ago or more. Hey, thanks to my patrons for their support. Thank you for watching, and we'll talk to you next time.
Pixel each frame, create new worlds of computerized brain, mazes and dungeons, dragons and kings, explore outer space and the ocean below. I'd never be bored.